Welcome to this demonstration interview.
We're going to be talking to you during the interview using Teams and at the same time using Miro so that we can both write things, both the interviewer and the interviewee, on the same whiteboard while we talk. And it's a really good idea to get some practice with using Miro. And if you can practice using the Miro whiteboard in advance of the interview, have a look at what you can do with the different functions. It'll help you feel more relaxed when the time comes. If the technology doesn't work, something goes wrong during the interview, then the main message is don't panic. The interviewer will know about that. You can tell them if you don't hear them, make them aware that you don't hear them properly, and we'll just go back to where we were and start again. Or in the worst case scenario, we'd talk to you again at another time when we managed to get everything sorted out. So really don't panic. In order to make it as likely as possible to succeed, then it's a good idea to have a good talk with your supporting teacher beforehand to make sure that your internet connection is nice and stable and that you have a quiet place to sit and you have everything you need at hand before the interview starts. And that might include some pen and paper next to you just in case.
In terms of what we're doing, really, we want to get the people who are best suited to this course onto this course. And we care about giving you every opportunity to do it. The key things are, it really doesn't matter what you know when you come in there, but we need you to be able to apply knowledge and to apply facts that we give you so that we can say that things are happening and we've got clear-cut evidence for what's going on around it. We're looking for how you solve problems, so we're not going to give you something to which there's a straightforward answer, where there's something where you immediately get where we're coming from. We might deliberately do things that contradict your knowledge of the world to see how you respond to evidence and how you deal with that. And we want to see how you put the jigsaw together. We want to see how, when you're looking at a question, how you connect facts together and how you apply what you're learning to the next bit of a problem. So we're not asking trick questions. We're asking you stuff where we're looking for you to provide evidence for your own abilities, evidence for what you can do. And there are going to be lots of ways to do that. So as you go along, think about what you're talking about.
We're not looking for any particular prior knowledge. We're not seeking to find those students who already know the most facts about chemistry. So how can you possibly prepare for such an interview? Well, there are several things you can do that will really help you to feel ready and relaxed and in the best possible position for your interview. Firstly, practice talking about chemistry and practice talking about reasons for things. Maybe you can talk to yourself in the mirror, or you can find someone in your family or some of your friends who won't mind listening as you explain out loud reasoning or explanations for some of the concepts that you've come across in your chemistry until now. Since we're going to be presenting you with material that you might not have seen before, it's useful to become familiar with handling different explanations or different concepts which might be somewhat at odds with what you've already seen in your schoolwork. So to prepare for that, maybe look up explanations for concepts or different ways of reasoning around the same sorts of material, perhaps looking in different textbooks to the ones you usually use. Having said that, we don't have any particular prior knowledge and we're not looking for the person who knows the most chemistry already, it's nonetheless really useful if you do revise and understand as best you possibly can all the material you have done at school so far, because these are going to be useful language and terminology that will come into the discussion. Of course, we don't mind telling you and explaining meanings for words when the interview comes, if you haven't encountered them already, but it's always good and we're always able to go further if a candidate has revised their schoolwork until now.
When you're in the mix and you're actually doing the interview, time is going to pass really quickly. You've got a lot of things to think about. I think the most important thing is that when you're doing stuff, try and talk about what you're doing. Don't just draw a picture and say nothing, and equally don't just say something and don't draw a picture if a picture will help you understand it. Talk through what you're doing. It helps the interviewer understand what you're thinking about. It helps you with where you're going. it's not always going to be something where you immediately get to the answer. Don't be surprised if you get stuck, and don't panic if you get stuck. The interviewers are there to prompt you as well as to ask you questions, and those prompts will hopefully lead you in the right direction. So keep going, keep thinking about it, and try and relax, and try not to take the stresses of the situation. Be calm, breathe. If you don't understand something, say that you don't understand. The world is full of people who claim to understand when they don't understand it. It's really important to say, I don't get this. It's an important skill for life, and it's an important skill for learning things. So it's legitimate not to know all the answers. We're there to help you explore what the answers might be.
Good morning, Charlie. Can you hear me okay?
Yeah, I can hear you. All good. All good.
That's great. Thank you so much for joining us for this interview. I'll begin by introducing us and telling you a bit about how the interview is going to run, and then we'll get started.
Okay.
And if at any point you can't hear us or you don't understand the words we're using, then just let us know and we can explain them a bit more clearly, okay?
Sounds good.
So my name's Susan Perkin. I'm a physical chemist, and my colleague is Professor Steve Faulkner, who's an inorganic chemist. And we're each going to ask you some questions in this interview.
Okay.
We're going to be using the Miro board. Would you like to just check that your pen works on the Miro board?
Yeah, I'll give it a go. There we go.
That looks great. Thank you very much. Now, the interview is going to be about 20 minutes long, and we're going to start with some questions from Steve. So I'll hand over to Steve now.
Thanks, Susan. Hi, Charlie.
Hiya.
Can you hear me all right?
Yeah, sounds good.
Good. Okay, so maybe we'll begin by thinking about something that I'm sure you've met before. Can you tell me a bit about water?
Yeah, so it's a polar molecule. I'll draw it out.
Yeah.
So it's got a bent shape due to the two lone pairs, with a bond angle of 104.5 degrees.
Okay. So you have this water molecule and it exists like that. What kinds of things can it do with those lone pairs?
So it can form hydrogen bonds. So that is an interaction where the lone pair is attracted to the delta positive hydrogen, which is a strong intermolecular force due to the polarity of the OH bond.
Okay. And that gives rise to lots of the properties of water, sure.
Yeah.
And you can think in terms of hydrogen bonding, and you can think about it being liquid and solid and a variety of other things.
Yeah.
Maybe let's start just by thinking about an H2O molecule all by itself. So we've got 3 atoms in that molecule.
Yeah.
And you've described it in terms of 2 bonds and 2 lone pairs.
Yes.
I want to think about it in terms of how we might make those bonds. So if we think about that, have you come across the concept of atomic orbitals before?
Yes, I have.
Okay. And you're happy with the idea that hydrogen has a 1s orbital that has an electron in it?
Yes.
And that oxygen can do its bonding through 2s and 2p orbitals?
Yes.
Yeah? Okay.
Yeah.
Have you seen the shapes of those orbitals before?
So the s orbital is spherical, so the hydrogen 1s would be spherical, and the oxygen p orbitals would be shaped like a normal p orbital would be shaped like that.
Okay.
Dumbbell.
Fair enough. Let me maybe try and paste something in here.
Okay.
And see if if we can successfully. Okay, so here are some pictures of some orbitals.
Yeah.
So really, we've got an oxygen atom.
Yes.
And we've got 2 hydrogen atoms, and they're going to be arranged in roughly the way you've drawn them.
Okay.
So we can say that there are 3 different p orbitals on oxygen.
Yeah.
And an s orbital.
Yes.
And we use this convention of saying that the orbital has different phase or different sign either side of the bit where you've got no electrons for p orbitals.
Yeah.
So there's
Okay.
a plane in which you don't find any electron density.
Okay.
So what I want to start to think about is how you might do bonding in that. Maybe if I explain a little bit first, that
Okay.
when a bond arises in a molecule, it arises because the electrons in one orbital interfere constructively with the electrons in an orbital on another atom, and you end up with more electron density between the nuclei, and that stabilizes the species that you've got.
Yeah.
It could work the other way around, that you could end up with less electron density between the nuclei, and then you'd have what's called an antibonding orbital.
Yeah.
I'm not going to worry about antibonding for now. I'm going to focus on bonding.
Okay.
So if we were to think about having, just draw your oxygen and your two hydrogens without a bond between them for a second.
Okay.
And we have something that you can see that looks like that. You've got a picture.
Yeah.
Let's put the 2s orbital onto the oxygen.
Okay.
Yeah.
Like this?
Yeah, that's fine. And if we put orbitals on the hydrogens, could we make them interfere constructively with that?
Would it look like that?
Try draw them around the hydrogens for now, yeah? Because
Okay.
you're getting to where you're going, but you're going in the right way, yeah? Just draw around one s orbital on the hydrogens, yeah?
Oh, yeah, I see.
Yeah.
I see. I've muddled the two. Hang on.
No, you're fine. You're doing all right.
So, like that.
Yeah. Okay. And in that case, all of those three atoms could interact with each other. Yeah?
Yeah.
And we're going to form something which is stronger than what we started with.
Okay.
Yeah?
Yeah.
So that's what we'd call the constructive interference. You're going to end up building up the electron density in the bit that you're drawing around at the moment.
Yeah.
Okay?
Okay.
So that combination of orbitals is giving rise to one bonding orbital.
Yeah.
Let's think about what else we could do. So in the way that I pasted the figure in, you've got p orbitals that point along x, y, and z.
Yes.
Yeah? And we're kind of defining the xz plane as being the plane of the paper and anything coming out of it. Yeah?
Yeah.
So if we were to draw your three atoms again, your oxygen and your two hydrogens.
Yeah.
Yeah, okay. So we've got those there. And we think about, let's start with the px orbital.
Okay.
The one that points left and right. Can you draw that?
From the oxygen?
Yeah, from the oxygen. Okay. Okay. Right, so now we've got a bit of an issue that when we did the orbital in the picture, that orbital is linear effectively. It follows the line of the x-axis. In drawing it to make it meet the hydrogens, you've made it bend. Yeah.
Okay.
So that might be where we're going, but it's got a problem in the getting there.
Yeah.
And it's got another little issue. If you look at the picture, you've got one side of it which is shaded and one side of it that isn't.
Yeah.
Yeah?
Yes.
And what we really want is for a shaded bit to match a shaded bit and for an unshaded bit to match an unshaded bit.
Okay.
So if we were to draw that p orbital,
yeah,
how could we arrange hydrogens so that we've got a shaded one on one side and an unshaded one on the other?
Okay. So I'll start again. I'll go here.
Yeah, okay.
So call that the shaded end.
Yeah, okay.
And then
So maybe just draw it horizontal for now, just to.
okay. Yeah,
you don't have to point it at the atoms. Yeah. So draw it the way it's drawn in the picture. Yeah. That's it. that's good. And then maybe shade one side of it. Okay.
That's right.
Right. So what would you have to do to that right-hand hydrogen to make it work?
Shade that in as well.
Yeah. Okay.
Yeah.
What about on the left-hand side?
So if it when it bonds to the other hydrogen, it's going to be a separate p orbital.
No, well, not necessarily. Just stick with this p orbital for now.
Okay.
Yeah. So we're mixing orbitals together. We're taking combinations of them, so we can play games. Yeah.
So for the other side, it's going to be a non-shaded.
Yeah. Okay.
Non-shaded.
Right. So that's pretty close to reality, apart from the fact that all of those orbitals are in a straight line.
Yes.
And what we're actually going to have is the two hydrogens offset downwards a bit, so it looks like H2O, aren't we?
Yeah.
Yeah. So what might be the consequence of offsetting it downwards a bit? Are the orbitals going to overlap just as well, or are they going to overlap less well?
I think they're going to overlap more.
But in the case of this one, it's going to be less, isn't it? Because as you move them away,
yeah,
as you go from having your oxygen and your two hydrogens being in a line to being offline, yeah, then we're going to get to the point that actually they don't point at each other, but those clouds fill space, so you're still going to get a favourable interaction. Yeah?
Yes.
Okay.
I see.
But if we're in the plane of those three atoms, let's look just briefly at the other two orbitals. Z pointing along the z-axis and Y pointing along the y-axis. So what could we say about the one that points along the z-axis? Could that help in bonding?
It's going to be perpendicular to the other p orbital.
Yeah.
So more in this plane, if there's no overlap, we're going to have...
Hang on, draw it up and down again. Let's keep the axes the same.
Okay.
So let's define a z-axis as going straight up there. Yeah?
Yeah. So you're going to have this.
Yeah, okay.
But you're also going to have...
And one side or the other is going to be shaded.
Yeah.
So let's shade the top. Yeah, that's good.
Yeah.
So what combination of hydrogens would we have to have at the bottom?
You'd have to have a shaded at the top and a
yeah, but there's no hydrogen at the top. The hydrogens are where those H's are.
Okay.
Yeah? So we'd have to have them both unshaded, wouldn't we?
Yes.
Yeah? So they're going to overlap together. Yeah?
Yeah.
And again, it's not going to be perfect. It's not going to be like the spherical orbitals on the oxygen. But it's going to be that you get some overlap and something favourable.
Okay. Yeah.
What about the last one? What about Y?
So pointing in that axis.
Yeah. Have you got a problem now? Because I think if it's going along that axis, what's going to be
the plane of the hydrogens?
Yeah. And the hydrogen orbitals have the same phase throughout.
Yeah.
So in front of it, you're going to see constructive interference.
Yeah.
And behind it, you're going to see destructive interference.
Yeah.
And that's not going to be good. So overall, you do nothing.
Okay.
So we've drawn this.
Yeah.
And you've got a bunch of orbitals. And in that bunch of orbitals, we've said, well, okay, s orbitals, lots of bonding. Yeah?
Yeah.
P, Y, for the sake of argument, no bonding at all. Yeah?
Yeah.
P, X, and Z, a bit of bonding. Yeah?
Yeah.
So in this model, all of those orbitals are going to have different energies, different degrees of bonding.
Yeah.
Does that fit with what you said originally? When you said you've got two lone pairs and two bonds?
Well, there's more repulsion from the lone pairs, but the bonds are equal in stability.
Yeah.
In my original drawing.
Yeah.
But
So
that doesn't match to.
Yeah.
No, that doesn't match to what we've just said.
Yeah, and we've only really got one lone pair.
Yeah.
So what? So and what we've described is true for an isolated water molecule.
Yes.
So why does your approximation stand up in the real world?
Because does it explain the shape of molecules better?
The shape's probably much the same. The shape is just the minimum energy.
Okay.
But what did we talk about when we were talking about water in solution? In your first figure that you drew?
It's polar.
Polar?
Yes.
And it's doing hydrogen bonding?
Yes.
Yeah?
Yeah.
So if we introduce lots of water molecules into the mix rather than just considering one, what's likely to happen?
They're likely to interact how I've shown.
Yeah, you're going to get an arrangement. So
yes.
Maybe that's a good point for me to swap to Susan.
Okay.
Okay?
Yeah.
Thank you.
Thank you.
Thanks, Steve, and well done, Charlie. Okay, we're going to continue with the thinking about water, because you've actually introduced to us that you've come across the concept of hydrogen bonding and interactions between water. So let's think more about water in the condensed phases. So that's to say liquid water and ice.
Okay.
So at atmospheric pressure, that's ambient pressure, water forms liquid and it can form ice depending on the temperature.
Yeah.
Do you know at what temperature liquid water and ice are at equilibrium?
Would it be 0 degrees Celsius?
Yeah, absolutely. And do you know what that is in Kelvin scale?
Is it 273? No, negative 2. No, 273. 273.
Yeah, absolutely right. And so I've just moved slightly to the right on the Miro board. I hope you'll see me drawing now. So if I were to draw a graph with pressure on this axis and temperature over here.
Yeah.
Do you see that?
Oh, yes, I can.
Yeah. So we could mark in 273 Kelvin down here, and we could mark in our atmospheric pressure. Let's call that 1 bar, standard pressure here. And so this is a point on the graph which represents the equilibrium between liquid and solid water.
Okay.
And if I were to increase the pressure of the surroundings,
Yeah.
do you know what would happen to the freezing point of water?
Would it decrease?
Yeah. Do you want to draw that on the graph, sketch a point which illustrates that? Absolutely. Yeah.
Yes.
Good. So in fact, for liquid water, although it's a very steep line, so we're going to exaggerate this curve, but there is a curve like this. And on the right-hand side of that, we have the liquid region, and over here we have the solid region.
Yeah.
We're just drawing a part of the phase diagram which is very close to the freezing point of water. So from this diagram, or from your knowledge, do you know which is more dense, liquid water or solid ice?
I think solid ice is more dense.
What makes you say that?
If pressure increases and which decreases the temperature, then so with molecules interacting, a higher temperature breaks the intermolecular forces. So at a higher pressure, if it's not solid, no, at a high pressure, if it turns solid earlier.
You're thinking really well there. I like the way you're thinking. If we imagine having some ice at the point where at the point where I'm marking now on the diagram.
Yeah.
So we've got some ice here, and we're going to increase the pressure
Yes.
of ice at constant temperature. So we're going up here.
Mhm.
At some point, by increasing the pressure, we can cause the ice to liquefy.
Yeah. Okay.
Does that help you? So we want to know which is more dense, the liquid or the solid.
So if increasing the pressure causes it to liquefy, that means the liquid is more dense because you're packing it tighter together.
Yeah,
It
absolutely.
has to be more dense.
Very good thinking. Thank you. That's right. And can you think of an everyday experience actually relating to water and ice at equilibrium that helps us to remember or visualize that ice is less dense than water around the ambient freezing point?
Ice expands, so water expands when it freezes.
Yeah, so when you see ice and water, for example, on a frozen lake or ice in a cold drink, the ice is at the top, it floats, doesn't it?
Yes.
So now let's get back to your sketch of water molecules, and you talked about hydrogen bonding as something that it can be acting between molecules. Yeah. And we've just thought about the fact that liquid water around this part of the phase diagram is more dense than the ice. Can you have us think through why that might be in relation to the hydrogen bonding? So have a go at sketching hydrogen bonding.
Yeah.
And how you think it might look in ice and how you think it might look in liquid water. And see if you can come up with an explanation for the difference in density.
So that's normal hydrogen bonding. So that'd be hydrogen bonding in liquid. Whereas in solid, they're fixed. So would it be, is it therefore harder for the molecules to move, to act on the hydrogen bonding if they're fixed into their position? Whereas in liquid, they'd be able to pack closer together because of the attraction.
I think you're thinking along the right lines, but let's just extend your diagram a bit. Could you sketch me a few more water molecules with hydrogen bonds? You told me some good information there about how the water molecules are more fixed in their positions in ice than in liquid water. So what I'm sketching here, which is a nice regular arrangement.
Yeah.
Do you think that's more likely to be a kind of structural motif that we would find in the ice or in the liquid water here?
I think that's more likely to happen in.
I mean, if we could extend it even more, so if we kept drawing it in the way that you've done here, or we could just imagine it carrying on in this nice symmetric way.
Okay.
Of course, it's tetrahedral, it's three-dimensional structure.
Yes.
So if we had a really uniform three-dimensional hydrogen bonding structure like that.
Yeah.
Do you think that would be the structure in the ice or in the liquid?
Would that be the structure in the liquid?
Why do you say that?
Because in a solid, I'd imagine it's more likely to be arranged in a more rigid almost, what's the word, lattice structure.
I think what you've drawn is quite a symmetric repeating lattice. Of course, we're drawing something in 2 dimensions, which is actually 3-dimensional, and they're actually, but in fact, in the ice, the hydrogen bonding is more ordered and is something like what you've sketched here.
Okay.
So in liquid water, I just want to check you can hear me okay, Charlie, because I know the connection is not great at the moment.
Yeah, I can hear you.
Still hear me, great. So in liquid water, the molecules are actually moving around all the time, aren't they? They're exchanging their positions and they're changing their orientations relative to one another, and they go from one place to another. So how do you think that influences the hydrogen bonding at any instant in time? If we could take a snapshot and have a little look at the hydrogen bonding at an instant in time.
So in a liquid, it wouldn't be as strong, because if it's constantly moving around, these attractions between molecules aren't fixed.
Yeah. Yeah. So in liquid water, the hydrogen bonds are present, but because the water molecules are moving all the time, then on average, only some of them are existing in the energetically most stable way. And just to make one more step of reasoning there, we talked about density, and you'll remember that you correctly told me that that the liquid water is more dense than the ice. So, and now we've also had this second bit of information, which is that in liquid water, not all the hydrogen bonding is in place, as it were. So not all water molecules have got 4 hydrogen bonds at any instant in liquid water. So putting those two together, can you help to rationalise why it is that liquid water is actually more dense?
Because they don't have these 4 hydrogen bonds at one time. Does that mean their arrangement, you can pack molecules tighter together? Yeah. Because they're not fixed.
Yeah, so the hydrogen bonds are actually quite long.
Dimensions, yeah.
Absolutely right. So the hydrogen bonding actually somehow forces the molecules to be very slightly further apart than they would be if they were packing more closely without so many hydrogen bonds as in liquid water. Absolutely right. Steve, did we have anything else we wanted to talk with Charlie about before we finish the interview?
I think that's pretty much covers me.
Yeah.
Do you have any questions for us, Charlie?
Yeah. You should feel free to add anything you wanted to say at this point or ask a question.
I'm just looking back at what we've done. No, I don't think I have any questions.
Well then, thank you very much for joining us, Charlie, for the interview.
Thank you very much.
Thank you. Okay, so that kind of interview that we've just gone through is fairly typical of what a Miro interview might look like. It contained opportunities to talk about things. It contained opportunities for the candidate to use the whiteboard and illustrate things. And it contained an opportunity to talk. So for my part of the question, I tend to believe that I only use questions in one admission cycle. So this is a question I've used before and I'm unlikely to use again. What I'm trying to see is how people respond to something that they haven't met before. In this case, we were talking about atomic and molecular orbitals, and we were talking in terms of how they might overlap. So Charlie began by thinking about something that he knew about. He looked at water, he described water well in terms of bond angle, in terms of shape, in terms of lone pairs. And then we went on to talk about orbitals, and he was a little bit familiar with the idea of atomic orbitals. And we moved into looking at how they might be fitted together and how they might make bonds between things. So in that, it involved discussing effectively spatial awareness within the molecule. And he picked up very quickly on the idea of where the bond ought to be. And in drawing the picture, initially he was fighting a frame of reference that he was trying to bring the orbitals into line with the atoms. And then we moved from that towards looking at bonding. And we talked through each of the possible bonding interactions for each of the possible orbitals. And we came to a place where we looked at the overall model and he realized it was different to what he'd started with. And then very briefly at the end of that, we discussed how the two models might be correlated in the real world and what might be happening. So that was my part of the question. Susan, do you want to talk about yours?
Yes, let's talk about the second part of the interview. I think Charlie did very well on this because he kept thinking clearly as we approached some new concepts for him. He was very well able to sketch the line on the phase diagram, and he did a good job of sketching hydrogen bonding as I prompted him through the question. It was clear that he hadn't encountered these concepts before, and that's actually what we always hope for in the interviews. If we have a sense that that the candidate has actually already been through this before, then we would try to move to something that's less familiar to them. And then once we're talking about something that's a little bit unfamiliar, we give some new information and help the student to use that to deduce something or to work through a problem. And Charlie did this very well. He was able to see how the repeating structure in the hydrogen bonding was eventually deduced that caused the ice to be slightly more expanded in its structure compared to liquid water, which is more compact. And we thought through that from a sort of thermodynamic point of view and incorporating observation that ice floats on water under ambient conditions, and also all the way from the molecular viewpoint of the hydrogen bonding, how those two things connect up. So he did very well in that and kept talking about what he was thinking. So overall, that was very representative of a typical admissions interview where we knuckle straight down to a physical problem and try to resolve something in that way.
And I think in terms of the general interview, it's pretty clear that Charlie is a good candidate. He's bringing in stuff. He's talking about what's going on. Yeah. The key thing in this is speaking about it, is saying that this is where we are and saying when you don't get it, because sometimes, because time is limited, it's really important to talk about how things fit together. So it's clear we both agree that this is somebody who has a grasp of chemistry, who can understand things, who can feel their way towards the issue of a problem. In terms of the rest, it's probably representative of what a normal interview would look like. It's clear that this technology helps you, but it's also vital that candidates need to talk about things and ask.
Absolutely, if there are connection problems, which we've even had some today, then we can just repeat ourselves and we can check that we can hear each other, so we can make sure that the technology's not getting in the way for us.
The other thing that it clearly illustrates is that there is no disadvantage to not knowing something. If you can work your way towards it, it's important to feel your way through the facts as you understand them. And if you can articulate that out loud, kind of one of the things that we're looking for, because the idea of the process that we're doing is it replicates aspects of small group teaching of, if you want to know about the things you don't understand, first of all, you need to be able to articulate what you don't understand. So all of that is important as you go through to say, okay, I don't get this. This is what I think. If somebody corrects you, how do you pick up on it? And I think that's something that Charlie did well.
I absolutely agree. Yeah. And in some cases, if you have some more advanced prior knowledge, it can sometimes even get mixed up with the thinking during the interview. So you have to be very careful to just listen to the information you're being given and talk about that alone. So for example, I think Charlie actually knew something a little bit more advanced about hybridization of orbitals, and he was bringing his actual prior knowledge of that into his sketches. Your part of the question, at a sort of stage ahead of, he was going in a slightly different direction to what you were trying to.
He was, and it's interesting because in one sense it represents another of these simplifications that builds the bigger world, but it doesn't represent the reality of what we're talking about. So sometimes there's a reason why we're asking the questions in the way we're asking them, and we want to see you being surprised by it.